Hi, and welcome to a Calculus 1 video where we discuss some derivatives as rates of change. So let's take a look. If you are following along with these videos, this is a part 2, sort of in a 3-part series. You had a pre-lesson where you did some algebra. Then we talked about the definition of the derivative and really developed that derivative idea from this graph right here. And we developed from that difference quotient and using a limit process what the definition of that derivative should be, bringing again h as close to 0 as possible so that my 2 points can virtually become 1, but I'm still able to calculate the slope, and that is where I get my slope of my tangent line instead of my slope of my secant line. And then also in a previous video we did some algebra. We used the algebra from number 1 in the previous video, and now we're going to use this algebra from number 2 in this video. So what I think I'd like you to do right now is, if you didn't watch that video prior, why don't you go ahead and either try this algebra on your own or pause the video or take a screen capture or something. This says find and simplify the difference quotient for this function. And we found the difference quotient. I gave you the difference quotient formula, and this highlighted ending here is what we ended up with. So if you haven't already, either work through this problem or add this to your notes. We are going to reference this here in a few minutes. Okay, so let's work through the second question here. We're asked to find f prime of a and f prime of 0 if this is our given function. So this is the same given function that we worked with in number 2 in that algebra, so we'll reference that when we need it. Right now, let's go ahead and set up our problem. So we are going to use the definition of a limit, and again, I'm going to work this through with x's, and then I'll substitute a in the end. So f prime of x equals, and I'm going to need a few different things here. So I'm going to eventually need that f of x plus h, so I'll write that out. And I would at this time also consider doing any algebra that I can. Well, the bummer is 1 over x plus h minus 5, that's it, because I substituted in x plus h in place of x. There's really no other simplification that I can do. So I'm going to leave that alone and just use it when I need it. This f of x in the difference quotient up here in this definition of the limit is my function, so that's fine, and all over h. So I think I'm ready to go. F prime of x is this limit. Again, without a limit, you don't have calculus. Calculus is the study of limits. Of f of x plus h, which I know to be this fraction right here, x plus h minus 5, minus your f of x, which was given, all over h. And this is where we insert all of the algebra that we did on that other page. And so what I'm going to do is copy down that right there, because that's what we're going to end up with. Now it is important to note that this is your chance to practice finding a derivative using the limit process, and you are expected to be able to evaluate all of these limits throughout the calculus course. And so let's not use, even if you know what the derivative rules are and you know, for example, quotient rule, let's not use that yet. We can use that later. So here's our limit process. I'm going to keep limit as h approaches 0, but I'm going to copy down what the difference quotient part simplified to from that previous problem. Now I can substitute 0 in for h because I have removed that discontinuity. So I'm going to not write down limit, but I am going to write f prime of x because that's going to carry down and name my function as a first derivative. But since I'm substituting in 0 for h, I don't have to write the limit at this point. So it'll be negative 1 over the quantity x minus 5 times the quantity x minus 5, which I can also write as f prime of x equals negative 1 over the quantity x minus 5 squared. Now again, they didn't ask me for f prime of x, they asked me for f prime of a. So I'll just substitute in the a instead of x. So there we are. And then they ask me for f prime of 0. And this doesn't get any more difficult, so no matter how many numeric derivatives they ask me for, no matter how many specific slopes of tangent lines they ask me for, at this point I'm just doing a substitution into that general derivative formula here. So that'll give me the slope of the tangent line to my function at any point along my curve. So now I want f prime of 0, so it's negative 1 over 0 minus 5 quantity squared. So f prime of 0 is negative 1 over 25, which means the slope of my tangent line at x equals 0 is negative 1 over 25. Okay, so these were two derivatives that we found, question 1 from the previous video and 2 from this video, in this section for defining the derivative or studying derivatives as rates of change. And so you're going to need to be able to replicate this process, again, using that limit notation, so you get a really good understanding of bringing that secant line in and becoming the tangent line. So going from an average rate of change to an instantaneous rate of change. So let's take a look at a couple graphs and see why we might be continuous at certain points but not have differentiability or not have the ability to differentiate or find a derivative there. Okay, so for now I'm going to give you two examples here. Y equals the cube root of x. So let me see if I can draw this. Something like so. Again, it's not perfect, but it'll get the job done. And this function is continuous at x equals 0. I have a point, so my function value has a value at 0, and my left limit equals my right limit. So my continuity exists at x equals 0. But why am I not differentiable at x equals 0? Well, differentiable is meaning I can evaluate the derivative, so I could find f prime of 0, which in other words says I can find the slope of the tangent line to the function at x equals 0. Can I? Well, let's look and see what that slope of the tangent line might look like. If we wanted to touch our point one time and also take the shape of the curve, the cube root's coming in pretty sharp. So maybe looking something like that. My tangent line actually looks vertical at that point, and my slope of a vertical line is undefined. So any sharp corner, turn, kink, or cusp, something that looks like this, I'm continuous at that point, but I am not differentiable, as well as our absolute value function. So let's take a look at that one. Give myself some space here. So our absolute value function looks something like so. And we've talked about this before, where the right-hand side is actually the line y equals 1x, and the left-hand side is actually y equals negative 1x. So I can see actually the slope of each line. But if I want to talk about that point right there at 0, 0, I am continuous at 0, 0. My left limit equals my right limit, which equals my function value. They're all 0. And so that works out for me, but I cannot evaluate the derivative there. Coming in, so right before that point, you're on this left side, you have a tangent line or a slope of negative 1. On the right side, just to the right of your point, you have a slope of positive 1. So what would your slope be here right in the middle? Again, some people might think it looks horizontal, some people might think it looks vertical, right? But it needs to take the shape of your curve, cross through one time, and it needs to tell you where your shape was and where it's going surrounding that point. Well, on one side I have negative, the other side I have positive. You might think it's 0, but it's too sharp of a turn. We have tangent lines with a slope of 0 approximately right here. And there's my horizontal tangent line. So it's not that I can't have a horizontal tangent line. Sure I can. That means f prime of whatever that x value is 0 at that point. Okay? That means the slope of my tangent line is 0. We will further investigate this as well when we talk about critical values and when we start graphing these curves in the next section and start looking at which is the curve of the original, which is the graph of the first derivative, and which is the graph of the second derivative. We might be having some of these same conversations again. Okay, last but not least for this section, I want you to understand some terminology. And again, if you understand the idea that a derivative is still a rate of change, it's just an instantaneous rate of change, the same types of labels will occur because a rate of change is just a slope, which is change in y over change in x, or our output over our input. And so when I'm looking at an initial position function, s of t, maybe that is in miles. And if I'm looking at my velocity, well, if I'm calling it a derivative, it's a rate of change. So my velocity label might be something like miles per hour, and I'm writing it out for a reason. And again, that's if t is in hours. It could be feet per second and all of that, but if our original function was in miles and t is in hours, then our velocity is our output, which was in miles, so change in y, over change in x. And then our acceleration is going to be the next derivative. It's going to be, I could also say that it's the first derivative of velocity. So it's either the second derivative of the original, or it's the first derivative if you have the velocity, because it's telling you how quickly is your rate changing. So for example, you saying that you're going 32 miles per hour does not actually tell me if you have your foot on the accelerator or if you have your foot on the brake. So if you then accelerate and you get to 33 miles per hour and 34 miles per hour and 35 miles per hour, etc., and your speed is increasing, then we can talk about that rate of increase of your speed. So we can talk about acceleration and what that means. So that's the second derivative. So looking at this maybe a little bit more clearly here, I have s of t, which is the original position, so maybe it's miles. I have velocity, which will be the first derivative, which might be in something like miles per hour. We're probably familiar with mph. And then if I take the derivative again, I'm at acceleration. It actually looks like miles per hour squared because it's miles per hour per hour. So it's how fast are you increasing your speed, for example. The next type might be a marginal cost type problem. And what this has to do with is if you are given a cost function, and I'll give you a very general example here in a second, the marginal cost is going to be the cost to produce one additional item, or in other words, the rate of change of the cost. So let's take a look at this. Okay, so if I have in general form a cost function for x, okay, I'm not going to write what it is. And if I say the cost to produce 100 items is $500. Let's say I'm going to produce t-shirts or something. I don't know. So I can give myself an average, right, based on that cost function, that on average, maybe this is in dollars and this is t-shirts. So maybe on average, it's going to cost me approximately $5 per shirt. Now, what we know is it probably cost me a lot more to create the first shirt because maybe I needed to buy the press or buy the building or buy the, 1,000 shirts at a time, whatever. So my first few costs are usually astronomical, and then it might level off over time. But what the first derivative is going to tell you is your slope of your tangent line at x equals 100. So if here is x equals 100, so this is my number of t-shirts, and this is going to be the cost function. So it might be, really high in the beginning and going lower, but again, I might raise it later because as you increase production, maybe your costs go up later. So at x equals 100, what is the slope of the tangent line right there? Okay, so that's telling me if I move over 1 unit, so to produce 1 additional unit, or 1 t-shirt in this case, what would it cost me? Okay, so it's calculating that rise over run. So maybe my C prime of 100 is 3. Well, let's say that I'm selling these shirts for, I don't know, $7 a shirt, okay? Maybe I'm perfectly okay with $3, so I keep producing. But then maybe somewhere along the way, I get to a marginal cost of, let's say I'm at 1,000 units, and I get to a marginal cost of 7, then maybe I say, you know what, stop producing because I'm really not making any money anymore. So that marginal cost idea can be based off of a cost function or cost graph or data, and it can help you determine as a business owner, for example, maybe when to continue production and when to stop production. So this is actually something that is studied a lot in a brief calc type course as well. So you have now velocity, so position, velocity, and acceleration, as well as total cost to produce your items and marginal cost, which would be the derivative. So you have some applications you might be working with as well. And I hope this video helps you sort of define the derivative a little bit more. Thanks for watching.